Good afternoon, everyone. Hope everyone's doing well. So today we start our discussion about the last couple topics of the course. Confidence intervals and hypothesis testing are going to be the last two topics that we consider together. Okay, so all told, this will cover a couple of chapters of material. I really am just going to be hitting the high points here, concerning ourselves primarily with population means. It turns out that we do have the tools to handle other population parameters like the variance, for instance, but that would involve more complicated distributions. And I really just want to expose you to the critical concepts here, not overwhelm you, and just give you an appreciation for how all of this stuff fits together. So let's talk about confidence intervals. Look at this beautiful pattern up here, right? Looks like wallpaper or something. Okay, so confidence intervals. So one thing that we will talk about is a new distribution in the context of confidence intervals called the student T distribution. More on that in just a moment, but we'll talk about confidence intervals, and we will need the student T distribution to support a full scoped dive into this topic. All right, so one thing that I'm constantly talking to you guys about is the fact that statistics is really a rough science that's trying to get at how a population is behaving, okay? So the population has parameters. The sample that you take from the population has statistics, and you can estimate population parameters with those statistics. And the question is, to what extent and how good of a job do our statistics do in telling us information about the underlying population parameters? Okay, so I mean, look, there would be no reason to do statistics at all if we just knew everything about the distribution of the underlying data at the beginning. We would just say, well, the mean is this, the variance is this. What probability do you want? We would compute it and we would be done. But the problem is, most of the time we don't know necessarily what the underlying distribution is. So that's why we resort to a statistical analysis of the situation at hand. So a picture that I hope you will have burned into your cognition once this course is done is the following. Okay, so here is the population, and the population has parameters, things like mu and sigma or sigma squared, right? So the population mean, population standard deviation, even things like rho, which we discussed. Okay, you know, rho is well, we discussed it in the Prob and Stats course. Rho is the correlation coefficient, but the main thing that we've focused on are mu and sigma. Okay, and populations can be unwieldy. It might be impossible to actually look at everything in the population and glean the mean and standard deviation from it. So what do? We take a sample. Okay, so and in this sample, so here's our sample. What do we get? Well, from the sample, we get statistics. Okay, we get statistics. So things like X bar, which is the sample mean, X bar, and maybe S, right? So S stands for the sample standard deviation. And incidentally, the size of the population is often denoted by capital N, okay? And the size of the sample is often denoted by lowercase n, all right? So from a sample, we get statistics. And those statistics those statistics are in theory supposed to be good estimates for the population parameters, okay? Sometimes we call, so like X bar is a point estimate for the population mean, and S is a point estimate for sigma. Okay, so these statistics approximate the parameters. This is why I kind of ranted that one time about, in sports, how we use the term statistics somewhat incorrectly, okay? It is possible that my sample from which I glean statistics happens to be the entire population, as it is in like basketball, for instance. So technically speaking, we're still talking about statistics there, but it would be more appropriate in that context to actually talk about population parameters as opposed to statistics. We know Michael Jordan's parameters, okay? We also know his statistics, all right, but a more accurate description there would be parameter in that case, okay? All right, so we collect a sample, find the mean X bar, which is hopefully a good estimate for mu. Okay, using sample data to generalize about a population is something that we call inferential statistics. Okay, we're making inferences, like we're drawing conclusions from the statistics that we get from our sample. Okay, so we're throwing a lot of terms around here, but these are things that we've been discussing together. Okay, so inferential statistics is what we're doing right now. Okay, so X bar estimates the population mean. Okay, now hopefully it's a good approximation, but in all likelihood, it's not going to be equal to the population mean. That would be very surprising if the sample mean was actually equal to the population mean. So if I really want to be more precise about, okay, what's going on with X bar, how good of an estimate is it for mu? What we're going to do is we're going to create an interval around X bar that we're fairly confident will contain the actual population mean. Okay, so what we're going to do is we're going to say, well, I got X bar. The likelihood that this is equal to the population mean, probably not very good. But if I make a little interval around X bar, then I start to get more confident that that interval actually contains the population mean. Okay, so this is kind of a picture I have in my mind. Okay, so like you get X bar. Okay, and then what you do is you form a little interval. Okay, so we'll call this X bar plus capital E. That's a pretty typical notation for the standard error of the estimate. Okay, and X bar minus E. And the question is, when I make that interval, is mu in there? Is mu in that interval? And we want to be certain with a fairly high probability that mu actually belongs to that interval. Okay, so just so you know, this E right here is often referred to as the standard error of the estimate. What estimate? Well, the estimate X bar. Okay, so X bar is always going to be right in the middle of our confidence interval that we construct. And that makes sense because all we have to work with is basically X bar and anything else that we can form from our sample. Things like the standard, the sample standard deviation, for instance. Okay, so that's what a confidence interval is, intuitively speaking. And let's see how this kind of works out in practice. Okay, so here we go. Well, first off, okay, what continuous distributions have we seen? Well, some of the more famous ones would be like the uniform, the exponential, and the normal distribution, yes. Discrete ones, well, things like the Poisson, the binomial, right? We've worked with all sorts of both discrete and continuous distributions. But now we want to talk about a new one, namely the student t distribution. Okay, the student t distribution is going to be the next distribution we're going to discuss. This is a continuous, it's a continuous distribution. So it's going to be another continuous distribution that we're going to heap onto the pile of ones that we already know things about. Okay. So here's how the student t distribution came about. There was a guy named William Gossett who happened to work for Guinness Brewing Company. Okay, you've probably heard that name before. I believe it's in Dublin, Ireland. Okay, and he actually was the first person to say, well, okay, maybe we don't know that the underlying distribution is exactly normal, but it kind of has a shape that looks basically normal. Maybe it's a little bit fatter in the tails than like the normal distribution is. And it was him thinking in this along these lines that he actually came up with this thing called the student t distribution. Okay. Mainly it was him analyzing how sample mean as a random variable and the sample standard deviation as a random variable, how those two things interacted with one another. Okay. And the Guinness Brewing Company required that anytime an employee, one of their research and development employees, wrote an academic paper, that they had to use a pen name. And he used the name student. There's speculation about why Guinness did that. One rationale is that they just didn't want their competitors to know what it was they were doing in research and development. So that's why this thing is called the student t distribution. But really, it was invented by William Gossett in the early 20th century. All right. So like I said, the graph is similar to the standard normal. The mean is 0, and it's going to be symmetric about x equal to 0. But the thing is, the spread of this thing isn't going to be necessarily always the same. It's going to be different depending on the situation. Okay, so we had the standard normal, which had a standard deviation of 1. The student t distribution looks like the standard normal. It's kind of, a bell-shaped distribution about 0, but the standard deviation depends on the situation at hand. In fact, the smaller the sample size that you have, the flatter it is. It's more spread out. That's because we have less certainty if my sample size is small. Small sample size means that the t distribution corresponding to it is going to be more spread out. Okay, that's because we just have less certainty about the underlying distribution. Okay, it has more probability in the tails than the standard normal does. It's more spread out. But as my sample size increases, this thing is going to get closer and closer and closer to the standard normal distribution. Okay, the shape of the graph and sigma, well, the shape of the graph is basically always symmetric, but and kind of spread out, and lives essentially in the middle part underneath the standard normal, but on the ends where the tails are, it's fatter. Okay, and we'll look at a picture of this in just a minute. But the key concept here is something called the degrees of freedom. Okay, I'm not going to get into the specifics of why it's called degrees of freedom per se, but it's always one less than the sample size, right? So the number of degrees of freedom is one less than the sample size. Once you know the degrees of freedom, you know the shape of the corresponding student t distribution. A small number of degrees of freedom means a flatter looking distribution. It's going to be flatter with more probability in the tails. A higher number of degrees of freedom means that the thing is going to start to look more like the standard normal, and there's going to be less probability in the tails. But let's go ahead and go have a look at a picture of what's going on here. So here's what that link on that slide actually took us to. I can't believe I'm saying this, but there's actually a fantastic Wikipedia page devoted to the student t-distribution. It really is fantastic. It even has examples, discusses a lot of the things that I've been discussing already in this lecture. It even talks about William Gossett right there, right? The individual that invented this thing. And here's what the distribution looks like. Look over here, okay? So here's this. So what's going on? New, okay, so let me just kind of circle this right here. That's the Greek letter nu, okay? So this is nu, okay? Mu was the mean. Nu is what you use for degrees of freedom. And that's always equal to one less than the sample size, okay? So look at what's going on with these student t-distributions. They're all kind of centered at x equal to 0, like we said, okay? But look, I mean, if there's only 1 degree of freedom, you see the yellow curve, that thing is kind of lower in the middle and fatter on the tails. And the higher the degrees of freedom are, like 2, see the purple curve kind of, right? It shrunk down in the tails and it humped up a little bit more in the middle. The blue is 5 degrees of freedom, which, by the way, 5 degrees of freedom means 6 sample size. So you see that, the picture of that curve. And then nu equal to infinity means that I've just let my sample size get arbitrarily large. That's the black curve. That's the standard normal distribution right there. Okay, standard normal. The black curve right there. So the t-distribution kind of approaches the t-distributions. There are infinitely many of them depending on the degrees of freedom, but those things are going to approach the standard normal distribution from below. Okay? So that's what the t-distribution looks like. All right. So back in our slide presentation here. So again, the shape of the graph and sigma depend on the degrees of freedom. And remember what Wikipedia was doing is it was letting this equal to nu, right? It looks like a V, but it's a little bit fancier than that. Okay, looks like a script V of some kind. That is the Greek letter nu. Okay, and again, that Wikipedia page is really great. There's a lot of good information about the student t-distribution over there. Okay, so here's some notation. If we have a random variable, capital T, that has the student t-distribution for some number of degrees of freedom, we write T is distributed as, we write the standard, tilde or twiddle as I call it. And then you write little t for a student t-distribution, sub n minus 1. And again, that sub n minus 1, just to remind you again, that is nu. Yeah, so that sub n minus 1, that is the Greek letter nu. That is the degrees of freedom. Okay. All right. Unfortunately, the density for the student t-distribution is ridiculous. Okay, it's very complicated. Probabilities are found using tables or technology. Okay, so let's go have a look at what the table looks like for these things. And again, it's just so that you know, everything that I'm kind of going out to other than Excel is right there on that Wikipedia page. It's a fantastic resource for sure. Here we are back over here on this Wikipedia page. First of all, here's the density function right here. Okay, looks sort of awful, right? It makes use of something called the gamma function, which some of you have seen, I'm sure. This thing is horrendous to try to integrate. Okay, so technology is used to compute various values. There are some things that you can actually, there are some ways to compute this thing by hand, but it is extremely unpleasant. But there's the distribution, which is a mess, like I said. Okay, and there's some nice pictures here as well that are not unlike what we saw above. okay, on this Wikipedia page. So for instance, if you look here, how is this thing working? Well, okay, so the blue plot here, and they say it right up here, the standard normal distribution, right? It says the standard normal distribution is in blue. And then they show the new degree of freedom t distribution in red, and they leave the old plots for that were at degrees of freedom prior. They kind of put those in green as they develop this thing. So for instance, the first graph right here, is for 1 degree of freedom. That's the red curve. And the blue curve is the standard normal. And you can kind of see what's happening. 2 degrees of freedom, that's the red curve. Okay, so this is, right, that curve right there is nu equal to 2. And the green curve is nu equal to 1. Okay, that's the old one. And as you can see, as you kind of increase the number of degrees of freedom, the curve gets closer and closer and closer from below in the middle and from above on the tails. Those t distributions get closer and closer to the standard normal. Okay, look at 30 degrees of freedom. It's like you're almost indistinguishable. Know what I'm saying? That's one reason why, to invoke the central limit theorem, 30, a minimum of a 30 sample size is usually enough to tame the most ridiculous distributions. That is not totally unconnected to the fact that 30 degrees of freedom, the student t distribution with 30 degrees of freedom is almost indistinguishable from the standard normal. Okay, but moving on here, I wanted to show you this table down here. They have lots of examples in here, by the way, which is super helpful. Even with confidence intervals, which we'll be looking at here pretty soon. Everything you could ever want to know about the student t distribution is on this page. Fairly amazing, including this table, if I can ever scroll down to it. Here it is. Okay, so this is in general how the table looks for the student t distribution. And it's the reverse of what was going on with the standard normal distribution tables. Okay, so that's kind of annoying. So what is going on here? Well, so what they have is a one-sided distribution and a two-sided distribution, whatever that means, okay? So the two-sided, basically what they've done for the two-sided is they have something like this, okay? So they've basically, oh man, let me redraw that. So for the two-sided situation, it looks like this. Okay, again, zeros right in the middle. Okay, there's my student t distribution. And in essence, what they are giving you is this percentage that's kind of symmetrical about 0 and has eliminated something from the same amount of probability from the two tails. Okay, that's what the two-sided situation is doing. What is the one-sided situation doing? Well, it's doing this. Okay, it's having 0 in the middle, and essentially what it's doing is it's just hacking off the upper tail and giving you this probability, everything below that thing. Okay, so I mean that kind of makes sense, because look, if this was 50%, okay, so if this was 50%, then how much would be in each one of these tails? Well, there would be 25% here, and there would be 25% here. So if I went to one-sided and just got rid of that left cutoff, then what percentage would there be? Like if this was supposedly the copy of the same situation over here on the right, then all of a sudden I would have 25% here. And what percent would I have below? Well, there would be 75%. Okay, so that's why you have 20 or 75% for the one-sided, and then they have 50% for the two-sided situation. Okay, and that makes sense of why it says 80%, 60%. Because if I have 60% kind of So 30% on one side of 0 and 30% on the other side of 0. That means I have 20% in each tail. So if I get rid of one of those tails, I'm now going to have 80%. Hopefully that kind of makes sense. Okay. So like 70% and 85%. That means like 70%, so 35% on each side of 0. That means I have 15% in each tail. That's 30% divided by 2. Okay. So if I got rid of one of those tails and just took one-sided probability, that would add an additional 15%. That's how that's working. You're basically always adding in half of the tail area to go to the one-sided situation. That's the relationship between those. And then essentially what these things are telling us, so like if I was at 6, for instance, 6, these things down the left-hand side are the degrees of freedom, right? So if this was new, okay, then if this was new and I was wanting to, if this was new and I look at this guy right here, 0.718, that's what this value would be right here, 0.718. So what would this guy be down below? Well, it's symmetrically the same, negative 0.718. Okay. Yeah. So that little t value for 6 degrees of freedom, it tells you the value such that, down above negative 0.718 and below 0.718, I have 50% of the data. And notice as I get big, as I try to increase the percentage, the t value gets bigger and bigger and bigger. That's kind of the cutoff point. All right. So by the way, in this particular case, 0.718, which is if I had new is equal to 6, that's kind of the situation I'm working with right here, is degrees of freedom equal to 6. I would have 75% of the data below that. Okay. Let me, so remember that number, 6 degrees of freedom, 75% below this value, or 50% between that value and the negative of that value. I'm going to go over into Excel and show you how this works over there. Okay, so I'll be right back. All right, here we are in good old Excel, and we just want to verify that our thinking was spot on over there in that table. Turns out Excel can give you all of the same information. So what I've done here is I've said, look, suppose we're at 6 degrees of freedom. By the way, that means our sample size is 7. You know what I'm saying? The degrees of freedom is always 1 less than the sample size. We're saying that capital T has the, capital T has what? Capital T has the student T distribution with 6 degrees of freedom. We wanted a value little t such that the probability that capital T is less than or equal to little t is equal to 0.75. So that means 75% of the data is to the left of this thing. And we said, look, because the t distributions are symmetrical, that if I go from t down to minus t, since I know 25% of the data is above little t, then if I go to minus t, 25% of the data is below negative t, and therefore the probability that capital T is between those two cutoffs is going to be 50%. So little t is really the 75th percentile. Yeah, we've talked about that before. So let's kind of think about how we would find this. So what is t going to be equal to, right? T equals to what? Well, what do we do? Well, we go equals t. Look, there's all sorts of things. There's t dist 2t, t dist RT. Really what we want is, since we want to have a particular percentage, it seems like what I want is inv, right? The inverse of this thing, okay? So what does this say? This is saying, hand me a probability, and again, this is going to be the inverse of the cumulative distribution function, okay? The inverse of the cumulative distribution function. So give me a probability. How much probability do I want to the left of this? Well, 0.75. What's our degrees of freedom? Well, 6, okay? and 0.718, which is exactly what that table gave us. We had 0.718 before, okay? So watch this. Let's just kind of check this out. Look, if I go equals, equals t distribution, okay, what's our x value, the thing we're going to go up to, that's our little t. So let's go 0.718, degrees of freedom 6, cumulative yes. We should get basically 75%, and we do, right? Okay, so there's that. There are some other options that we saw here though. So what were they? It was like equals t inverse 2 tail. Okay, so there was t inverse and there was t inverse 2 tail. Well, in this case, what's going on? I wanted like 50% in the 2 tail case. Okay, so 0.5, degrees of freedom 6. And this isn't all that revealing just because in this case we actually had 50% in the 2 tails also, but this will give us the same value. Okay, this will give us the exact same value. So let me just to show you a situation that's not as trivial. So watch this. What if I went equals t dist or t inverse like this, and let's say I wanted to have 80% below this thing, 80%. So 0.8, and degrees of freedom, let's say 6, okay? I get the number 0.9, or 0.9 is the cutoff point, okay, 0.9. Okay, and this was the 80th percentile. Let's see, I'll just put that this is 80th. This is the 80th percentile. Okay, 80th percentile for what? For degrees of freedom equal to 6. Okay. And okay, so if I wanted the 80th percentile, this means 80% below this value, I get 0.95 whatever. Okay, so what would that mean? How much is there in each one of the tails? Well, or how much is there above this thing? 20%. Okay, so what would the percentage be if I wanted to actually have a symmetric cutoff? Okay, like a 2-tail cutoff. There's 20% above this, then there would basically be 20% in the left tail as well that would get cut off. Okay, so watch this. This right here is the probability. So in other words, the probability that t is less than or equal to 0.906. Okay, what is that going to be? That's going to be equal to, let me move this over so that it makes, so that it's, so it looks a little bit nicer. Okay, so this is equal to t distribution. Okay, what's my x? 0.906, degrees of freedom 6, cumulative yes. Okay, and I get 80%. 80%. Okay, but again, what if I wanted it to be a 2-tail situation? Okay, so you know that the probability that like negative 0.906 is less than or equal to t is less than or equal to 0.906. Okay, since I have this symmetry in the t distribution and it was 80% below it, that means 20% was above. So if I reflect across, I'm chopping off a 20% in the left tail of this thing. Okay, so what's that going to be? Well, it should be roughly what? 60%. So let's check that out. So equals t distribution. Let's do the 2-tail situation here. 2-tail situation. What's our x? 0.906, degrees of freedom 6. And that is, that's giving me the percentage of data that's in the 2 tails. I see. So this is giving me the percentage of data that happens to be in the 2 tails, which is 40% in that particular case. Okay. So yeah, there you go. Right. So in other words, what's happening here is this is not the probability that t is between these two things. That's the probability. That's the opposite of that. 40% is in the tails. All right. Right. So 60% is right there. So this is 1 minus that is actually equal to 40%. Okay. And another way that you could have gotten the 0.906 is you could have used the t inverse two-tail thing, and you could have said, okay, how much probability do you want in the two tails? How much probability do you want in the two tails? Well, what do you think? In this particular case, we would want, if there's 20% above, 20% in the left tail, we want 40% split between the two tails. Okay, and the degrees of freedom are 6. We should get the exact same number, 0.906, and we do. Okay, so there you go. These computations in Excel are done in terms of the probability that happens to be in the tails. Okay, so I just wanted that to be clear from the get-go here. Okay. Okay, back here in our presentation. Hopefully we have a good idea of what's going on with the student t. Well, we're going to be using this a little bit more later, but just wanted to give you a basic introduction to the student t distribution so that you really understand what's happening once we start using it. Okay. So again, I just want to do a brief introduction to how confidence intervals are going to work. And then we'll come back next time and finish off this discussion. So in theory, a good estimate for mu should be x bar, but we know full well that it's probably not going to be precise. Okay. So in the end, this is just a repeat of something we said before. We want to be like 95% confident. Okay. In theory, we would like to be in a situation where we're some percentage of the time confident that we have an interval around x bar that contains the actual population mean. And that interval will be called a confidence interval. Okay. So that's the goal. So like, here's a typical situation that you might find yourself in. So assume that the scores on a Calc 1 final for all 150 students are known to be normally distributed with a standard deviation of 7, right? That's for the whole population. Okay. X is a test score for one random student. Okay, and suppose I've graded 30 tests so far, and the average and standard deviation for the sample, right? So these are the sample mean and the sample standard deviation, right? For the sample is 80% and 5 respectively. So in other words, you know, x bar is equal to 80 and s is equal to 5. Okay, I want to estimate the average for the whole population. What is the point estimate? Since I don't know the population mean, the point estimate would just be x bar equals 80. And I would hope and pray that that was pretty close to the true population mean. But in all actuality, it's not likely to be equal to the population mean. So that's why we want to resort to doing an interval estimate for this thing, okay? And how do we do it? Well, like this. Essentially, this is it. This is what you do. You take the sample mean. Remember I said the thing about, you know, going x bar plus or minus some number and then wanting to have the mean be in that interval of values. Well, here is the interval. It's going to be x bar minus 1.96, and this 1.96 is tightly connected to this 95% confidence interval thing. Okay, basically 1.96, what that means in essence is basically 2 standard deviations. Okay, and you know that within 2 standard deviations of the mean, if you have basically bell-shaped curve, you're going to have 95% of the data. That's where that 1.96 comes from. You go down by 1.96 times sigma over the square root of n, where n is the sample size, and you add 1.96 sigma times the square root of n. That will be an effective confidence interval in the case where you know the population standard deviation, which honestly isn't going to be all that likely, but this is kind of the formula for this thing. Okay, I'm not going to do, I'm already kind of, this thing's getting lengthy just because I talked a lot about the student t distribution. I'm going to leave it at this for now. We have our formula for our first formula for a confidence interval. We're going to have other ones that actually involve the student t distribution. And actually next time I'm going to show you where this formula came from. And not surprisingly, the formula comes from the central limit theorem. So the derivation of this is going to involve the central limit theorem in all of its glory. Okay? All right. I'm going to pause it here, and that is going to be all for today.